Hello everyone, my name is Dam Quang Nam. I am the third year PhD student at ABC, University Paris Cité. In this talk, I will present my work about the noise characterization for the stochastic gravitational background data analysis. I hope everyone have been familiar with LISA. This is the space-based gravitational wave detector, which will complement to the other detector in order to broaden the gravitational wave spectrum in frequency. The LISA will be sensitive to various astrophysical and cosmological sources, including the stochastic gravitational background. The origin of the stochastic gravitational backgrounds could be coming from the unresolved astrophysical sources and also possibly the cosmological sources. There is two main questions for searching the stochastic background. The first one is to extract the overall shape of the stochastic gravitational background within the LISA frequency band. And the second question is to break it into the individual components. And that will be very challenging due to the fact that there are various components contribute to the stochastic background, and some of them we don't really know the shape in frequency, the spectral shape. And also we need to take care about the instrumental noise in the data, because it could be impact to the signal reconstruction, as we see later. And our study will be focused on the first question for searching the stochastic background. Let's see the overall shape, and also to test the what is the impact of the noise characterization to the stochastic background signal reconstruction. Because since LISA we launched in 2034, we need to develop some simulator for generating the data. And here in our study, we can have the two possible data generation pipeline, either in time or frequency domain. To generate the L1 data, the TDI, the time-delay interferometry variables, AET, in second generation. And in this talk, I will focus on the frequency data generation pipeline, because it will be easier to control the data flow for the full pipeline, including the generation and analysis pipelines. And here in the following is the schematic for the data generation pipeline. I use a generator called the SGWB data to generate the simulated L1 data in frequency. And the input for this generator is the noise model, as well as the template for the stochastic background and the foreground. For the noise model, we can use the 2 or 3 noise parameter models, and in the configuration of the equal arm length and the same noise level for every same kind noises in all spectra. Each noise component has a specific noise shape, noise level, and the TDI transfer function. But for the next step in the data analysis, we will fit only the noise level of the noise component, and assuming we already know the shape and the TDI transfer function. The extra noise term in the 3 noise parameter models have been taken into account for the different propagation of the optical measurement system noises going through the different interferometric measurement in the LISA instrumental model, and also for the TDI algorithm. This plot is showing the difference between the 2 noise model in the spectrum sensitivity for the TT combination. And we see that the difference between 2 noise model are mostly at the high frequency of the LISA band, and the maximum of the difference is about 20%, 25%. And this is the comparison between the 2 noise model for the AA combination. So now I will talk about the data analysis pipeline we are using to search the stochastic gravitational background. We use the tool called the SGWBinner, which has been developed by Mauro Pieroni and also other college. The idea of the SGWBinner is to search the stochastic gravitational background signal for the small beams, which are the small equal log frequency intervals, and assuming that the signal inside each beam will be just a single power law, and they are independent for every beam. So we can use the SGWBinner to reconstruct the stochastic gravitational background signal independently on the model. The noise and the foreground are fit globally in the whole frequency band, assuming that the foreground templates are the same as for the data analysis are the same as the data generation pipeline. So we already know the foreground shape. And for the noise model, we could use the 2 or 3 noise parameter noise model. And the noise model using the data analysis could be different from the data generation. We use the TT channel combination to constrain the nuclear for the noise parameter because the gravitational wave as dramatically suppressed in the TT combination. And we use the AA channel combination to estimate the signal and the noise parameter with the noise level coming from the TT constraint above. The parameter estimation is based on the Bayesian inference, and we use the AIC, the IKK information criterion, to decide whether we merge two nearby bins or not. And after finishing merging process, we can estimate the uncertainty of the signal and noise reconstruction. And this final step can be run within the MCMC sampler to have more accurate estimation. And here is the schematic to show the data analysis pipeline as described before in the previous slide. We have the simulated L1 data in frequency at the input to fit the SGWBinner, and the full data in frequency will be going through the binning process to split the data into the several data bins, and each data bins will be going through the parameter estimation to estimate the signal and noise parameter, the IIC for each bins, and then going through the binning process. And if the IIC is not fulfilled, we will merge some bins, nearby bins, and go back into the parameter estimation process. And if all the IIC has been fulfilled for every bins, we can go to the final output. That are the parameter estimated parameters with the error for all bins. And we can run the MCMC for the final step. So here are some results I have with the SGWBinner data analysis, SGWB data analysis. With the correct noise model in data analysis and data generation pipelines. For example, I use the 3 noise parameter models for both, and the data including the signal in the single power shape, and this shape is coming from the Stochastic Gravitational Background foreground from the stellar origin black hole binaries. And as shown in the following plot, in the right hand side, in the left hand side, that's the reconstruction plot, and we see that we have reconstruction, the simulated data indicated as the red at the blue dot here very well. The sensitivity has been reconstruction as the green line here matched with the data, so we have been reconstruction well the noise. And for the signal, we have the input signal as indicated as the blue dash line here, and we have been reconstruction it pretty well as well, indicated as the yellow curve. And in the right hand side, that is the posterior distribution for the signal parameter in the 2 first column, and the last 3 one are the noise parameter estimation, and all of the estimated parameter are compatible with the true value, the input parameter for the data generation, indicated as the red dot line here. We also run the SGWBinner for the case with the data set, including the signal and the foreground, galactic foreground. And as the following reconstruction plot, we see that we have been reconstructed the noise, the foreground, and the signal very well. And in the right hand side, that is the posterior distribution for all parameters, and they are all compatible with the true value. In the case, we use a different noise model for data generation and data analysis pipelines. We obtain the worsened reconstruction result as shown in the following plot. I used the 10 initial number of bins for the SGWBinner, and finally we got the 5 merge bins, and each merge bin have the signal reconstruction, but the signal reconstruction are totally different, mismatch to the input signal shape. And that's because we use the inaccurate noise model for the reconstruction that leads to the underestimated noise, and this could be contribute to the wrong signal reconstruction. In the right hand side, that is the posterior distribution for the noise parameters, and we see that there is some bias. There is a bias in the P noise parameter estimation. To check again our conclusion above, we also run the SGWBinner for noise only data, so we don't include any signal in the data, but still with the wrong noise model between the data analysis pipeline and data generation pipeline, we obtain the wrong signal reconstruction as a following reconstruction plot, and there is bias in the P parameter estimation. So here's conclusions. The Stochastic Gravitational Background is one of the main objectives for the LISA mission to answer various questions about the astrophysics and cosmology. We have been developed and updated the data analysis tool to search the stochastic background in frequency band, and this is independently on the stochastic gravitational background models, and we reconstruct the signal in parallel with the noise and the foreground. We see that the more accurate knowledge of the noise characterization, we obtain more reliable signal reconstruction. And in the future step, we could use the time domain data generation pipeline with a more realistic LISA configuration, such as the different arm length, noise correlation, or non-stationarity. And there's an open question to investigate the possibility to reconstruct the signal and the noise with the agnostic noise model or more generic one. Thank you for your attention. I'm happy to answer any question in the chat.